Okay, so L'Hopital's rule. Right, and this is another technique for evaluating limits. If you know the technique, we're going to try to see where it comes from. So I'll write the theorem first. We're not going to, it has multiple different cases. We're not going to prove every possible case of it, but we'll do one or two of them to get the idea where this result comes from at least. So let us first write it down. So we have two functions that are differentiable, okay, on some open set. And G prime has no zeros in this interval, except possibly at x naught. Okay, so what we're mostly trying to exclude when we do this is something that would be basically constant in the denominator, and then you take derivative of it in the denominator, and you get just something that's basically 0 in the denominator, which would be bad. Okay, but G prime might approach 0 at this point x naught, and that's okay. Okay, so then we're going to suppose that either of these two things is true. Okay, so either both f and g are approaching 0, or they're both approaching infinity. So either this one or f of x goes to plus or minus infinity, and g of x also goes to plus or minus infinity. And we suppose that if we were to take derivatives of these two things, then the ratio of those derivatives would have a limit. Suppose that the limit as x goes to x naught of f prime of x divided by g prime of x is equal to L. Okay, and we're going to allow that L could be either a finite number or it could be plus or minus infinity. Okay, so where L could be finite or infinite. But it's something that we can definitely evaluate. Okay, then the theorem says, well, you know what the theorem says, that we can use this limit here to get the limit of our original ratio f over g. So then the limit as x goes to x naught of f over g is also equal to L. Okay, so this is the theorem. This should be familiar to you. Now we want to try to get some intuition and some rigorous argument for why this actually works. So this is going to be the basic strategy. Again, I'm not going to do all the possible cases, right? Because you might have to do different things depending on if this is finite or infinite, different things depending on if this is 0 or infinity. But the arguments are going to be similar, but have to be adapted a little bit in every case. So this is our strategy. We're going to take the limit from the left and the limit from the right and handle them separately. Right, so we know at x naught, potentially things go wrong. Certainly, we have a 0 over 0 form at x naught. So we're going to try to come at it from the left and see what happens. We're going to try to come at it from the right and see what happens. And if we get the same thing coming at it from both directions, then that means we've got an actual limit. Okay, so let's do the left and right-hand limits separately. Okay, I'm only going to argue one of these. We'll do the left-hand limit. The argument for the right-hand limit is completely identical. And let's start with one particular case. Let's start with the 0 over 0 case and assume that we have a limit L that is some finite number. Okay, so I'm going to suppose this. One particular case of, we have these limits, x goes to x naught from the left of f of x is equal to 0, which is the same as x going to x naught from the left of g of x. Okay, and we're going to assume L is finite. Okay, so what do we want? We have a theorem that we're trying to prove, and it says something about how the object we want involves function values, the limit of function values, and we're going to try to put it in terms of something that involves the derivative of these functions. So maybe the first question I'll ask is, do we know anything about relating function values to the derivative of functions? Yeah.
The definition of the derivative.
Okay, the definition of the derivative uses the values of functions. Yeah. What else? What other results do we have that relate function values and derivatives? Mean value theorem, right? So we have a mean value theorem that says we're talking about function values. We can put this in terms of the derivative somewhere. We're going to try to use something like the mean value theorem here. We need something a little bit different because we don't have one function. We have two functions we're playing with here. So what we need is a generalization of mean value theorem that's going to work with two functions floating around. So we know we want to relate function values to derivatives. Okay, the mean value theorem does this. But again, we need this generalization. But we need a version of it that works for two functions. Okay, so this is going to be called Cauchy's mean value theorem, or a generalized mean value theorem, where again we have multiple functions floating around. So let's call this the Cauchy mean value theorem, MVT. So we'll think of this as a little lemma that we're proving on the way to trying to get L'Hopital's rule. So it's a little result that on its own, maybe it's interesting, maybe it's not, but it's going to be useful for us to try to get to L'Hopital's rule, which is interesting and useful for us right now. Okay, so let's let f and g be continuous on our interval AB and differentiable on the open set. Okay, then this says there exists some value in the interval, so some number c. Okay, such that f of b minus f of a, so this is the kind of difference that we expect to show up, times g prime c is equal to, and then we're going to have something symmetric on the right-hand side. We're going to have a difference of our g's, g of b minus g of a times f prime of c. Okay, if you wave your hands a little bit, this looks reasonable, or at least not unreasonable probably, because if I were to divide this side by b minus a and this side by b minus a, so this over b minus a would look like an f prime times g prime. This over b minus a would look kind of like a g prime times f prime. So it looks not unreasonable, but that's a sloppy argument because now I've used the same c for both of these, right? We've got to refine it a little bit, but sanity checks along the way are nice. This doesn't look completely insane. But let's see if we can do something a little bit more rigorous. So what I'm going to do is try to look at a difference between these two things. So I still want to use my mean value theorem to prove this, right? We already have proved a mean value theorem about relating functions to derivatives. As always, we want to use the old work that we've already done. That just means what I need is one single function that I can apply the mean value theorem to. And where I'm going to get my single function is to look almost at the difference between these two things. But I'm going to drop the primes here, right? So here, c is the thing that's getting plugged into the derivative. I want that to be the same c that comes up when I use my actual mean value theorem. So I'm going to try looking at this kind of difference. Okay, so what I'm going to do is I'm going to leave these as constants, and I'm going to change these to g of x and this to f of x, so that when I take derivatives, I'll get a g prime, f prime, and hopefully c gets plugged in there. There's a goal. So let's look at the difference. We're going to define it as a function. F of b minus f of a times g of x minus g of b minus g of a f of x. Okay, this is just a constant times g of x and a constant times f of x, right? This is just a number here out in front. And that means that since f and g are continuous and differentiable, this function is also going to be continuous and differentiable, right? Satisfies all the conditions I need to use the mean value theorem, the regular old mean value theorem. Okay, so this is certainly continuous on AB and differentiable on the interior. Okay, so what does that tell us? That tells us we can use the mean value theorem. The regular mean value theorem, because this is just a single function of x, tells us there exists some c in the interval such that h prime of c is equal to h of b minus h of a over b minus a. Yes, we believe this part? Okay, so now it's just a matter of plugging things in and doing the calculations, right? We know what h is. We can compute the derivative of h, and we can plug in these a's and b's where we need to. Okay, so if I look at the left-hand side, h prime of c, that means that f of b minus f of a, this is just a constant. Take a derivative, I get g prime of c minus g of b minus g of a times f prime of c. That's my h prime of c there. Okay, and this is going to be equal to this ratio here. Okay, so what is that equal to? That is f of b minus f of a, g of b minus g of b minus g of a, f of b. That's my h of b minus my h of a. So fb minus fa, g of a plus g of b minus g of a f of a, all of this divided by b minus a. And if you stare at this for just a moment, we realize that this can simplify quite a bit, right? In fact, it's going to simplify to 0. All we've got are just these different products of f and g evaluated at either b or a, and we get this nice symmetry when we work it out. So this is actually 0. And that's good because that gives us exactly what we want. That gives us the result of our Cauchy mean value theorem. If we rearrange this and set the left-hand side equal to 0, exactly this pops out. Exactly that f of b minus f of a g prime c equals g of b minus g of a f prime c. That's exactly what we wanted. Questions there? Right. It's a more complicated result than the mean value theorem, but the proof is easy because we can use the results that we already have. Okay, so what's our goal? Our goal is to use this result that says I have two functions. I can relate function values to the derivatives, and I want to use this to go back to trying to prove something about L'Hopital's rule. So we're going back to L'Hopital's rule with the 0 over 0 form. And we have a goal. Our goal is to show something about the limit of f over g, that is equal to L. So it's good to always remember where we're trying to go with this. So our goal is to show that the limit as x goes to x naught, okay, we're just doing from the left right now, of f over g is equal to L. So if that's my goal, what do you expect the first line of my proof to be? Let me rephrase. What does it mean for this limit to equal L?
Be equal to the limit of the derivative.
Okay, we want to show it's equal to the limit of the derivative, but for now L is just some number. What does it mean for this limit to equal L? There's an epsilon delta definition. Okay, so what's the first line of my proof? Let's choose an epsilon greater than 0. Yeah, it's not a trick question. So every time you're asked to show some limit is equal to something else, almost always your first line of your proof is to say, let's choose an epsilon greater than 0. Right? And we're going to try to show that we can satisfy the definition of the limit. In other words, f over g minus L can be made less than epsilon as long as we keep x within a little delta neighborhood of x naught, and we only have to come at x naught from the left right now. Okay, so we have picked our epsilon. We need to show there's some delta out there. Any ideas where I could find a delta? So we're working towards our goal. I also said one of our big proof techniques is just to write down the things we know. What are the things we know?
So there's a delta bounding the limit, the other limit.
The other limit. So we have another limit that popped up. It's erased now. We knew that the limit of f prime over g prime was equal to L, right? That was something that was given in the hypotheses of the theorem. And so we can write down exactly what that means. It's always worth doing. Take the information you're given and write down precisely what that means. So we know that the limit as x goes to x naught, okay, I'll say from the left, but actually from both directions, of f prime over g prime is equal to L. Okay, and if I write down exactly what that means that for any epsilon greater than 0, including this one that we've already picked, we can find a delta. So we know there exists a delta greater than 0 such that if x is sufficiently close to x naught and to the left of it, because right now we're trying to do a limit from the left. So I'm going to say if x naught minus delta is less than x is less than x naught. Right, so we're within a delta window of it, but only coming at it from the left right now. Then automatically we know that f prime of x over g prime of x minus L is going to be less than epsilon in magnitude. We agree with this? All right, so now I'm going to try to pull out, I've written down basically what I know. Now I'm going to try to pull out my generalized mean value theorem because it's kind of the one tool in my toolbox right now that lets me relate derivatives to function values. So what does that mean? That means I'm going to actually need an x and a y in this interval, right? Because the x and the y are going to function as my a and my b here. Right? So I'm going to choose an x and y that live in this little delta window and try to use my Cauchy mean value theorem. So let's choose x and y in this little delta neighborhood. Okay, and we're going to let them serve as my a and b in this Cauchy mean value theorem. Okay, my Cauchy mean value theorem says there lives, so I have x, right? So here, let's just draw a little timeline of what we've got here. There's x naught minus delta. Now I've picked some x and some y in here, wherever they are. And my Cauchy mean value theorem says, okay, this is serving as my a and this is serving as my b. There exists some value c in between them, where I can apply my Cauchy mean value theorem. So we know there exists some c, which is also in this delta neighborhood. Such that, okay, and then I'm going to write down the results of my Cauchy mean value theorem, right? Exactly this, but now we have x and y instead of a and b. Okay, so such that g of x minus g of y times f prime c equals f of x minus f of y times g prime c. Okay, it would be great to rearrange these a little bit. So if I could rearrange this to say if I could divide out the g prime and divide out this, I'd have an f prime of c over g prime of c, right? I could solve for f prime of c over g prime of c. Since c lives in my little window, I could use this result here, that f prime of c over g prime of c minus L is less than epsilon. Okay, so we know that f prime of c over g prime of c minus L is less than epsilon. right? That works because C lives in this delta window. You agree with this? Are you comfortable with this? Everybody's avoiding eye contact. Right? So this delta window said that I can pick any number that the fact that we have this limit of f prime over g prime says I can pick any number, any value in this window, and I can plug it in here into f prime over g prime, and I'm going to be close to L. I'm going to be within epsilon of L. That's what it means for that thing to have this limit. Now I've said, all right, I've chosen a number that I want to plug into this thing. I've chosen the number C. I look at it. Yep, indeed, it lives in this little delta window. So that means C is a valid choice to plug into here and know that f prime over g prime is close to L. It's within my epsilon tolerance of L. So what I would really like to do is say f prime over g prime is equal to this difference minus this difference. Anything that could go wrong there? We don't want to divide by 0, right? So we know what we'd like to say. I would like to say this, right? Because that would let me replace this thing that involves derivatives with something that involves function values, and we're trying to get back to function values. So I would like to say that f prime over g prime is equal to f of x minus f of y over g of x minus g of y. We're worried that we're going to divide by 0. So we've got to think about this a little bit. Is there any danger that we're going to divide by 0? If g of x is equal to g of y, I might divide by 0. Exactly. So is there any danger that g of x is equal to g of y? I heard a no from somewhere. Why not?
Because there's no point between x and y where the derivative of g is 0.
The derivative of g is not 0 in between them, exactly. So we had, one of our hypotheses was that in this window, as long as things are tight enough, g prime is never 0 except possibly at this point, right? But not nearby. And that's what's going to save g of x and g of y from becoming equal to each other. So let's make an argument. If that happened, then by Rolle's theorem, we'd have a point in here where g prime was equal to 0. So then g prime of, say, d would equal 0 for some d between x and y. That's Rolle's theorem. And we know that this doesn't happen. So we said this was one of the details that we wrote down in the theorem. It's a detail that you might not have seen written down carefully before, that g prime is not allowed to vanish near x naught. Right? Well, in other words, basically g is not allowed to be flat near x naught, which makes sense when we're taking its derivative and sticking this in the denominator. So we say, but from the hypothesis of our theorem, okay, this can't happen. at least as long as delta is small enough, right? So this cannot happen as long as delta is small enough. Okay, in other words, g of x minus g of y is definitely not 0, and we're safe here. So I can go back to this and say, whew, this was actually valid. When I divided out g of x minus g of y, I didn't create any new issues for myself because I was just dividing out a number, and the number was not 0. And everything else was safe here. Again, f prime over g prime we knew we could handle because we knew this thing had a limit. So that was safe. Okay, so in other words, I can say it is true that f prime of c over g prime of c is equal to f of x minus f of y over g of x minus g of y. And there was nothing special about how I chose x and y here. I said, let's just take any x and any y in this interval. So we'll just make it clear. We'll emphasize that. And this can be done for absolutely any choice of x and y in our little delta neighborhood. So for any choice of x and y in the delta neighborhood.
Such that they're distinct, right? They have to
Such that they're distinct.
Correct.
Yeah. Stick that in there. Distinct choice. Okay, so this is good. This means I can come back to this estimate, right? We wrote down the one of the very few things we knew, which was that f prime over g prime had a limit. And now, in place of f prime over g prime in here, I can write this quotient that involves the function values. And this is good because we are trying to work our way back towards something that relates function values to this limit L. Okay, so I'm about to erase this, but I'm going to use this fact in my very next line. Okay, so this means that f of x minus f of y over g of x minus g of y minus L is less than epsilon. Okay, and again, this works for every distinct xy such that x naught minus delta is less than x and y is less than x naught. So this is getting close to what we want. What I'd really like is just to have f over g and not have this extra little bit subtracted off. Can I get there? How can I get there? So let's go back to our theorem again. What else do I know? As we go to x naught from the left, the values of f and g vanish. So what I'm going to do is this. I'm going to keep x fixed, wherever it is, and I'm going to start taking y closer and closer to x naught. So we know that the limit as y goes to x naught from the left of f of x of f of y is equal to 0, which also happens to be the limit of g of y. The marker is getting too light, yes. Okay, so we know that we can take these limits, that these guys are going to go to 0. So I'm going to straight out take the limit of both sides of this inequality. The one thing that happens when I take the limit of both sides of an inequality is this might have to become a less than or equal to in the limit, right? Because we might have a bunch of things. They're always less than, less than, less than, less than. But in the limit, they might actually approach epsilon, for example. So if I take the limit of both sides of my inequality, okay, as y is going to x naught from the left, what do I get? I get f of x minus 0 divided by g of x minus 0 minus L is less than or equal to. All right, epsilon is a constant. He doesn't depend on y at all, so he's just going to continue to be epsilon. And this is always going to hold as long as x lives within this little delta window. And this looks good. This is exactly what we wanted to show, right? We wanted to show that we could keep, that as long as we picked a suitable delta, kept x close enough to x naught, we could keep f over g close to L within some tolerance that we've chosen. And we've managed to do that now. So this is exactly the statement that the limit as x goes to x naught from the left of f of x over g of x is equal to L. Questions on that? Right, now what we could then do is make exactly the same argument coming at x naught from the right. I'm not going to write any of that down because there's absolutely nothing different about that argument. The only thing that happens is this picture gets flipped. So I'm going to say, using exactly the same argument, exactly the same reasoning, gives that the limit from the right of f of x over g of x is also equal to L. Right? And I had to split it up. The reason I had to split it up was because we knew we could have problems at x naught. Right? G prime could vanish at x naught, and that would have broken the argument I was trying to make. Would have broken the fact that g of x minus g of y, right, could actually be equal to each other right at this point. So that's why we had to split things up. But there was nothing special really about coming at it from the left as opposed to coming at it from the right. So this works the same way. And then we can conclude, well, if the limit from the left is L, the limit from the right is L, then we've got a limit. So the limit of f of x over g of x is equal to L. And that is at least one case of L'Hopital's rule, the 0 over 0 case, where we have a finite limit. Any questions there? So the proof is a little bit longer, but it uses the tools that we're building up. And obviously it's a powerful way of letting us evaluate limits relatively easily, complicated limits relatively easily, without having to go back to the definition of the limit every time with complicated functions. So if I were to do an example like this, the limit as x approaches 0 of sine x over x. Well, I'd look at this and I'd say, right, this guy goes to 0, this guy goes to 0. So this looks like a nice time to pull out L'Hopital's rule. Take the derivatives of both sides, and we get 1. Right, standard example from first year calculus. Here's a slightly more interesting example. So the limit as x goes to 0 of x minus x squared sine of 1 over x divided by sine of x. Okay, so we look at this, and again, clearly the denominator is going to 0. Numerator is also going to 0, right? Because, okay, this term goes to 0. This term is bounded by 1, and it's multiplied by something going to 0. So this term goes to 0. So again, this looks like the kind of form where we'd like to use L'Hopital's rule. So if I do that, what do I get? I get a 1 minus 2x sine of 1 over x. Okay, then here I take the derivative of this guy. I get minus 1 over x squared coming out. So that's plus cosine 1 over x. The numerator divided by cosine of x. What's that limit equal to? Should be 0? Why should it be 0? What does this guy do? He oscillates back and forth. Right? So what is this whole limit equal to? It doesn't exist. Question. Is this the right answer? I started with this thing, and I tried L'Hopital's rule, and I got that the limit doesn't exist. Is that right, or is it wrong? Jake, you're shaking your head. Why is it wrong? You want me to take more derivatives? We're not in, also this guy is not in a domain where L'Hopital's rule holds, right? Because the numerator doesn't go to 0, it doesn't go to infinity, right? So, yeah.
L'Hopital's rule assumes that the limit of the derivatives is in the extended rules.
Exactly. So L'Hopital's rule, one of the hypotheses was that when we did this, when we wrote down f prime over g prime, we'd get a limit that was either finite or plus or minus infinity. It doesn't tell us what happens if f prime over g prime does not have any limit at all. So this is actually not a valid use of L'Hopital's rule here. So L'Hopital's rule only works if the limit as x goes to x naught of f prime over g prime exists or is infinite, right? It tells us nothing about what happens if that limit doesn't exist. So this is my warning. Whenever you want to use a theorem, definitely, I encourage you always, definitely use the theorems that we've already proved in class, because you don't want to prove everything from first principles every time. But make sure the theorem applies, right? So we wrote down some hypotheses. one was that basically g is not a constant function. G prime isn't just vanishing. But another important one was that we could compute this limit as either a finite number or infinity. If those hypotheses don't hold, then the conclusions of the theorem don't hold. They don't tell us anything. So in fact, if we try this limit again, I'm going to rewrite this a little bit. So we know when we're taking limits, we don't care what happens at x equals 0. We care what happens close to x equals 0. So I'm going to rewrite this a little bit as the limit as x goes to 0. And I'm just going to divide out an x from the top and the bottom. 1 minus x sine 1 over x divided by sine x divided by x. Now, these are both perfectly valid things, right? Again, I'm only interested in what happens near x equals 0, not at x equals 0. And in fact, both of these limits exist. So I can use the limit laws that we have to say this is the same as the quotient of these limits. And what is this limit actually equal to? It's equal to 1, right? So again, here's 1. 0 times something that stays bounded by 1. This guy over here, limit of sine x over x, which we actually just did over here. My quick toy example was not to teach you how to use L'Hopital's rule, but actually just so that it would be written on the board at this point. And we could say we know this is 1. So this limit is actually equal to 1, right? We can compute the limit. It's finite. It's not what we would get if we tried to use or misuse L'Hopital's rule here. Right? So that's just a caution, which keep in mind for this theorem and for every other theorem we do in class, that these theorems are powerful. They're great. You should use them. But make sure you're using them in the right context. Yep.
If you had sine of 1 over x in the denominator, would that also be invalid because you couldn't find a region where the derivative was non-zero in the bottom?
So if I had sine of 1 over x in the denominator, then the thing in the denominator, yeah, the limit would not exist. Yeah, and that's right. You wouldn't be able to find a region where it was not 0. Yeah, so there's subtleties. In all of math, there's subtleties. And you don't want to let the subtleties paralyze you and make you scared to ever use these theorems, but you want to be careful and just know that they're there. Okay, I'm going to make a little bit of an argument also for the infinity over infinity case, just to see where that goes differently. So let's also consider the limit as x goes to x naught of f of x equals infinity. The same for g of x. I'm going to just assume they're both positive infinity here, just to make the algebra a little bit simpler. But again, you can generalize this. So most of the reasoning is going to go the same as it did before. I'm still going to assume that L is finite here. Oh, sorry. Yeah, L is finite. Let's keep L finite. So f prime over g prime, that has a definite limit. That's just a number. It's 1 or 0 or 3 or whatever it is. So most of the argument is going to go exactly the same way that it did before. Where things are going to get different is where we get to the stage where we want to make sure that we're not accidentally dividing by 0. So let me again draw a little cartoon out here. So I have maybe x naught here. we have f going to infinity. It doesn't have to go straight up to infinity. It could oscillate on its way there. That's fine. But we know that for any value we pick, right, eventually it's going to stay above that value. That's what it means for the limit to go to infinity. So for this case, I could say I can find some x value of x1 such that if x is between x1 and x0, then certainly f and g are bigger than 0. Right? So out here, it may be negative at some point, but eventually I'm going to say, I'm going to put a line here. Because this thing goes to infinity, eventually this thing gets above this line and it stays above this line. It may still oscillate, but it's not going to come back below this line. So I might say, here's my x1. And as long as we're to the right of x1, as long as we're between here and here, f and g are positive. Then I can say, oh, okay, it's positive, it's some value. And I could draw a new line here. And again say, as long as x is big enough, right, as long as we're close enough to x0, we're always going to stay above this line. So again, that's what it means for the limit to be infinite. That no matter what value I put here, eventually f of x is going to be bigger than that value. So I could find another x2 over here. So I can always find some x2 such that if x belongs to x2 and x0, then f of x is going to be bigger than f of x1, and g of x is going to be bigger than g of x1. Okay, and now I should be in business to use my mean value theorem and feel pretty safe. So the mean value theorem says there exists C belonging to x1 and x such that f prime of C over g prime of C is equal to f of x minus f of x1 over g of x minus g of x1. Okay, and this is going to work for any choice of x that's bigger than x2. So this is my x. So for any choice of x belonging to x2 to x0. Right, because we know that as long as x is in this interval here, it's above this line that's set at f of x1. Okay, so mean value theorem lets me do this, and I'm not dividing by 0. Okay, so this is important. This is not equal to 0. And the reason it's not equal to 0 is because g of x is definitely bigger than g of x1. So before, right, in the 0 over 0 case, I just picked any x and y in my interval, and I didn't worry too much about it. Here I had to be a little bit more careful to make sure I'm not dividing out a 0. But again, we can still do it. We can fix our x1 and let x get close to this x0.
Why couldn't we use the same argument as before?
Why couldn't we use the same argument as before? So it's not so clear here that we don't have this oscillation back to the same value again.
Okay.
Right? So for if I just pick any value in this interval, say x, right, it's always possible that somewhere else in this interval will oscillate back down to that value. We don't have anything here in our theorem that's necessarily telling us that can't happen. Yeah?
The graph there, is that the graph of f or the ratio?
This is a graph of f, for example.
Well, we care about when g of x, when the denominator is 0, right?
We care about when, well, now we're taking things to infinity.
Mm-hmm.
Right? So this is a different case, I guess, than what we had before.
Yeah.
Right? But the key is, right, we can always do this. We don't need to make special arguments about what the derivative of g is doing. We just need to know that because this thing blows up, that's all I need, right? That's all I need to know, that I can always get above any level that I want. Pick a point here, pick the function value here. I can always find a point later on where we're guaranteed to stay above this value. Okay, again, we know that f prime over g prime we can control. Okay, so let's try to rearrange this a little bit. All right, so I'm going to write this as f prime of c over g prime of c is equal to f of x over g of x. I'm just factoring this out. Times 1 minus f of x1 over f of x. And 1 minus g of x1 over g of x. Okay, or if I solve for this f over g, this is going to be f prime c over g prime of c times the reciprocal of this guy here, 1 minus g of x1 over g of x, 1 minus f of x1 over f of x. And I'm going to call this capital F of x, just to keep from having to write it all the time. All right, so we know that this is close to L, right? Same reason it was before. F prime over g prime is close to L within this epsilon tolerance of L. What value is this close to? This is close to 1, exactly. So let's say that x1 is fixed. I've taken x somewhere out here. And again, I'm going to let x approach x naught. As x approaches x naught, this goes to infinity. This goes to infinity, right? G and f are just at x1. G of x1 and f of x1 are just fixed numbers. So we can notice that the limit as x goes to x naught of f of x is equal to 1. Right? And that works since the limit as x goes to x naught of f of x is infinity, and same for g of x. Okay, so what happens when I take the limit of this thing as x goes to x naught? Well, we can try to work it out. So f of x minus g of x, sorry, over g of x minus L. Right, this is f prime of c over g prime of c times f of x, capital F of x, minus L. And I'm going to use the mathematician's favorite trick of adding 0 to things and try to break this up into pieces that are really easy to estimate and to keep small, because we want this at the end of the day to be small. Agreed? We're trying to show f of x over g of x minus L is less than something small, something like epsilon or something that depends on epsilon. So let's try to rearrange this a little bit. So I have f prime of c over g prime of c. I have capital F of x. What would be reasonable to put here, to add or subtract here? Something that we could control, that we could keep small. Okay, you want a delta. So I want to actually just look at f of x, capital F of x. What do we know about this thing? It's close to 1, right? So that means capital F of x minus 1, that should be small. So that we expect to be small. That means, of course, I have to add back the thing I subtracted off. And I still have that minus L floating around. And I can do my good old triangle inequality, and I can say this is less than or equal to this ratio times f of x minus 1 plus, minus 1 plus f prime of c over g prime of c minus L. Right, and these are things we know the limits of. This we know approaches L. This we know approaches 1. That means this term is small. This we know approaches L. That means this term is small. So I can say, for small enough values of delta, if x is within this little delta neighborhood, I'm going to have that capital F of x minus 1 is less than epsilon, and I'm going to have that f prime over g prime minus L is less than epsilon. Right, and what's the biggest that f prime over g prime itself could be? So we know it's close to L, right? It's approaching L, but it could be a little bigger than it. What's the biggest it could be? Keeping in mind L plus epsilon, right? It's close to L. It's not exactly L. It's not necessarily less than L, but it doesn't differ from L by more than epsilon. So this we know is less than L plus epsilon. And that means if I put all this together, so I go back to, the left-hand side, which I just erased. That means that f of x over g of x minus L is going to be less than, this is bounded by L plus epsilon. This is bounded by epsilon. This is bounded by epsilon. And this is good enough to show that we have a limit. So this is not quite the way we're used to our proofs ending, because we love it when we end with a nice clean epsilon on the right-hand side. I don't have a nice clean epsilon on the right-hand side, but what I do have is something that goes to 0 as epsilon goes to 0. In other words, I can make this is serving as my epsilon tolerance, I can make this as small as I want, just by taking epsilon as small as I want. So this can be made less than any tolerance I like. By taking epsilon small enough. And that's good enough. And it's good enough for your calculations too. Sometimes when you're computing limits, if they're a little more complicated, at the end of the day you'll get this thing minus L is less than 2 epsilon or something like that. You don't have to go back and rework your proof. That's good enough. As long as you have something on the right-hand side that goes to 0, as epsilon goes to 0, you know you can make it smaller than any tolerance. So, and this is something that you'll commonly encounter, that it's not straightforward to make this exactly equal to epsilon, but you can always make it as small as you like. So here I can already conclude that the limit as x goes to x naught from the left is equal to L. Okay, so that's the infinity over infinity case. It's very similar to the other case. There's a little bit more manipulation that has to happen along the way. But you can similarly do all the other cases, say where L is infinity. You can write down what these definitions mean and do these manipulations. Make sure use your mean value theorem. Make sure you're not dividing by 0 and argue your way there the same way. Right, and now this opens up lots of things that we can take limits of. Right, you know that you can manipulate other indeterminate forms. Can be manipulated often into this setting. Right, so if you have things that look like they're of the form 0 times infinity, infinity minus infinity, 0 to the infinity, things like this, infinity to the 0, etc. Right? You know from calculus that if you do some careful algebra, you can usually manipulate these into a form that looks like 0 over infinity, and then you're in business. You know that you can pass limits through continuous functions. All right, so for example, I'll do one. You've seen examples like this before. The limit as x goes to infinity of 1 plus 3x to the 1 over x. Right, this is an infinity to the 0 kind of form, which again is indeterminate. So your standard trick here is to take e to the log of this thing. So to say this is the same as taking the exponential of the logarithm of 1 plus 3x to the 1 over x. Right, and then even better, because we know things about continuous functions and how that relates to limits. Since the exponential function is a nice continuous function, this limit can pop into here. So this is the exponential of the limit of log of 1 plus 3x divided by x. Right, 1 over x comes down. And again, this works. Kind of thing that you did sloppily in first year calculus. This works because this is a continuous function, and because for continuous functions we have this rule about composition of continuous functions, right? What happens to limits when you're composing continuous functions? And the rule says that actually the limits can pop inside. So this works since the exponential function is continuous. Right, and now you're in business. Now you've got inside of here, okay, log of something that's going to infinity and an infinity over infinity kind of form. And now we're in business to try to use L'Hopital's rule, as long as when we take the derivatives we get something that makes sense. Okay, so this, the limit as x goes to infinity. What do we have? 3 over 1 plus 3x divided by 1. That's L'Hopital's rule. Right, which is valid because this limit makes sense. Okay, valid because the new limit makes sense. Right, and now you're in business to just evaluate the limit. You get e to the 0, which is 1. Okay, so this is L'Hopital's rule. Again, you can play with it, do lots of other cases. The important thing is just to make sure along the way that things are valid. And in a lot of most cases, things are valid. It's the pathological cases you have to watch out for. But those are the kind of things where you're going to get potentially g primes vanishing, where you're going to get limits that do not exist coming out, where you can immediately go back and say, that didn't work. Okay, so I'll leave you there.